Hello there, and welcome to the Sleep Science Calm Stories. I'm so glad you found your way here tonight. Maybe the day has been long. Maybe the room around you is quiet now. The lights low. The outside world beginning to settle into evening. Wherever you're listening from, you can simply allow this moment to slow down a little. There's nothing you need to keep track of here. Nothing you need to remember. The story will unfold gently on its own, and if your attention drifts at any point, that's perfectly fine. These ideas are patient. You can let them pass by like clouds, knowing you can always drift back whenever you like. Tonight, we're going to spend some quiet time exploring a place most of us rarely think about, a place that exists far beyond our skies, hidden among the stars of our galaxy, a place where new stars slowly begin. If you enjoy peaceful science like this, you're always welcome to subscribe to the channel and return whenever you'd like a quiet place to listen. Now, when most of us look up at the night sky, the stars appear steady and timeless. Small points of light scattered across the darkness. It's easy to imagine that they have always been there, shining quietly in the same positions, but the truth is something softer, and in many ways, much more beautiful. Every star in the sky began somewhere, long before it ever shone as a star, long before it produced warmth or light. It began as something far quieter, something much more delicate. It began inside a drifting cloud. These clouds are called nebulae, and across our galaxy, they are the quiet environments where new stars slowly take shape. Some nebulae glow softly in telescope images, their faint colors spreading across space like distant watercolor. Others remain almost completely dark, hidden against the background of the galaxy. But whether bright or invisible, they share something important in common. They are made of the raw material from which stars are born. Inside them, gas and dust drift slowly through space. Gravity pulls gently at that material, and over enormous stretches of time, those tiny motions begin to gather matter together. It is an incredibly patient process. Stars do not suddenly appear in a flash of light. They grow, they gather. They slowly take shape from clouds that may have been drifting quietly through the galaxy for millions of years. And the remarkable thing is that our own sun almost certainly began this way too, about 4.5 billion years ago, long before the Earth existed, long before oceans or forests or living creatures. Our sun was simply part of one of these clouds, a quiet nebula somewhere in the Milky Way and somewhere else in the galaxy tonight, far beyond the reach of our telescopes. The same process is still unfolding. New clouds are gathering. New stars are beginning. If you'd like, you can imagine drifting slowly through that larger landscape of the galaxy. Vast regions of space where clouds of gas move almost imperceptibly, spreading across distances that are difficult for the mind to grasp. And yet, within those clouds, something extraordinary is slowly happening. The very first stages of a star are beginning. The quiet clouds between the stars are not as empty as they first appear. When we imagine space, we often picture a perfect vacuum, a vast emptiness stretching between the bright islands of stars. But in reality, The space inside galaxies contains a thin, drifting mixture of gas and dust. It is extremely faint, so faint that in many places it would appear almost like nothing at all. In a typical region of this interstellar space, you might find only a few atoms in a cubic centimeter of volume. Compared with the dense air around us here on Earth, that is unimaginably sparse. But the key difference is scale. These clouds are enormous. A nebula can stretch across dozens of light years, sometimes hundreds. A single cloud may contain enough material to form thousands of stars over time, and the main ingredient inside these nebulae is hydrogen. Hydrogen is the simplest element in the universe. Each atom is made of just one proton and one electron. Yet, despite its simplicity, hydrogen is the building block of nearly every star. Inside a nebula, countless hydrogen atoms drift slowly through the darkness. They move gently, carried by faint currents of gas that weave their way through the galaxy. Most of the time, these atoms simply pass one another by. The space between them is enormous compared with their size, and so the cloud remains thin and quiet, almost ghost-like. But nebulae are not perfectly uniform. Some regions of the cloud are slightly denser than others. Perhaps a faint ripple of gas has gathered in one place. Perhaps the lingering shock wave from an ancient stellar explosion has compressed part of the cloud ever so slightly. From inside the cloud, these differences would be almost impossible to notice, but gravity notices them. Gravity is patient. It does not need force or speed. All it requires is time. Wherever a tiny concentration of matter appears, gravity pulls very gently on the surrounding gas. The effect is incredibly small at first. A subtle attraction between drifting particles, but over thousands of years, then millions. That pull begins to gather more material. A slightly denser region becomes just a little denser still. More atoms drift inward, more gas accumulates, and slowly, almost imperceptibly, a quiet change begins to take shape inside the cloud. The nebula that once seemed like an endless fog now contains tiny regions where matter is gathering together. These are the earliest hints of a star that does not yet exist. If you were somehow able to float inside such a cloud, you might not notice anything unusual at all. The darkness would be deep and cold. The gas would drift slowly around you, but hidden within that calm environment, gravity would already be at work, gently gathering atoms into new patterns. It's easy to miss how strange that really is. Across distances of trillions of kilometers, invisible forces are quietly drawing matter together. The building blocks of future stars are assembling themselves with extraordinary patience. And that quiet gathering is only the first step, because deeper inside some of these clouds, the gas becomes colder still. Cold enough for the atoms themselves to begin forming new bonds. And that subtle chemical change is what transforms an ordinary nebula into something even more remarkable. A molecular cloud, one of the coldest and most important environments in the entire galaxy, and will drift there next. And inside some of these quiet nebulae, something subtle begins to change. The gas grows colder. Not just cool in the ordinary sense, but cold in a way that is difficult to imagine from our everyday experience. Temperatures inside certain parts of a nebula can fall to only a few degrees above absolute zero, the coldest temperature physics allows. At these temperatures, motion slows dramatically. Atoms that once drifted freely through the cloud begin moving more gently. Their collisions become softer. Their paths through space become calmer and more deliberate. And in that deep cosmic cold, hydrogen atoms begin doing something important. They begin pairing together. Instead of remaining separate single atoms, two hydrogen atoms can attach and form a molecule, a pair known as molecular hydrogen. This may sound like a small change, but in the quiet chemistry of space, it marks the beginning of a very different environment. Regions where large amounts of molecular hydrogen form are known as molecular clouds. These clouds are darker, colder, and denser than the surrounding nebula. Light from nearby stars struggles to pass through them because the gas and dust inside absorbs and scatters the light. If you could somehow observe one from the inside, it might feel less like floating in open space and more like drifting through a faint, shadowy fog, not thick enough to see clearly, perhaps, but thick enough that distant starlight fades into a dim glow. And inside this quiet darkness, gravity continues its slow work. Molecular clouds are among the largest structures in our galaxy. Some of them contain enough material to form tens of thousands of stars. Yet, despite their enormous size, the internal motions inside these clouds remain very gentle. The cold temperature keeps the gas calm, preventing it from expanding too quickly. That calmness is important because when gas becomes cold and still enough, gravity finds it easier to gather the material together. Small fluctuations in density begin to matter more. Perhaps in one region of the cloud, the gas is just slightly thicker. Maybe a faint ripple of matter has drifted into the area. Or perhaps a distant shock wave from a long-ago supernova has compressed a portion of the cloud. At first, the difference might be incredibly small, but gravity, once again, is patient. Wherever the gas is just a little denser, its gravitational pull becomes slightly stronger than the surrounding regions, and that stronger pull attracts more gas toward it. Atoms drift inward, molecules follow. The dense region becomes slowly thicker. From the outside, nothing dramatic appears to be happening. The cloud still looks quiet and still, drifting slowly through the galaxy. But deep inside, gravity is quietly gathering material into small pockets. Astronomers sometimes refer to these pockets as density fluctuations. They are tiny irregularities within the cloud, slight knots where gas is beginning to collect. At first, they may span enormous distances, perhaps many times larger than our entire solar system. Yet compared with the vast size of the cloud itself, they are still small features, and over long stretches of time, these fluctuations grow. More molecules drift toward the center. The gas becomes thicker. The gravitational pull becomes stronger still. It's a little like watching a very slow snowfall inside an invisible sky. Individual particles drifting downward, gradually building a deeper layer. Except in this case, the snowfall lasts for hundreds of thousands of years. Eventually, the densest regions inside a molecular cloud reach a point where astronomers can clearly identify them as separate structures. These structures are known as dense cores. Dense cores are one of the most important stages in the life of a star. Inside a molecular cloud that may stretch across dozens of light years, a dense core might measure only a fraction of a light year across. Yet within that small region, the gas has become thick enough that gravity is beginning to take control of its future. The pressure from the surrounding gas can no longer easily hold the region in balance. Gravity begins to win, and when that happens, the core begins to collapse inward, not suddenly, not violently, but slowly, steadily, and with extraordinary patience. Gas from the outer parts of the core begins drifting toward the center. The inward motion is still incredibly gentle. It might take tens of thousands of years for the gas to move a noticeable distance, but once the process begins, it tends to continue. More gas falls inward. The central region becomes denser. Gravity strengthens further. The collapse feeds itself in a quiet cycle, and if you could somehow observe this process over millions of years, you would see the cloud slowly tightening, like a soft mist gradually gathering into a glowing seed. This stage is still completely hidden from ordinary sight. The dust inside the cloud blocks visible light, concealing the growing core from most telescopes. But modern instruments that observe in radio waves and infrared light can detect the faint signals of these regions. Through those observations, astronomers have found thousands of dense cores scattered across the molecular clouds of our galaxy. Each one is a potential star. Some will collapse into small stars, not very different from our sun. Others may form groups of stars that emerge together from the same cloud, and some dense cores may never quite gather enough mass to ignite a star at all, remaining quiet clumps of gas drifting through space. But when the conditions are right, when enough material gathers and gravity continues its slow pull, the collapse deepens. The core becomes denser, the inward motion grows stronger, and eventually, deep within that dark cloud of gas and dust, the very first stage of a new star begins to appear. Not yet a true star, not yet shining with nuclear fire, but something warmer, something faintly glowing, a protostar, the earliest heart of a future sun, and will drift closer to that moment next. As the collapse continues, the center of that dense core grows steadily warmer. This warming happens for a simple reason. When gas falls inward under gravity, the particles become more crowded together. Their motions become more energetic, and that increase in motion produces heat. It's not the heat of fire or flame. Nothing is burning yet. Instead, the heat comes from compression, the same basic effect you might feel if you quickly squeeze air inside a bicycle pump. The air grows warm because the molecules are being pressed together. Inside a collapsing dense core, that same principle unfolds on a vastly larger scale. More gas continues to fall inward. The center becomes denser. The temperature rises, and eventually, at the heart of the cloud, a small, glowing object begins to form. Astronomers call this stage a protostar. A protostar is not yet a fully formed star. It has not started the nuclear fusion that will eventually power it for millions or billions of years. But it is already something new. It is a young object where gravity has gathered enough material that the central region has become warm and luminous. The glow comes not from fusion, but from the energy released as gas continues falling onto the forming star. In a sense, gravity itself is producing the light. Deep inside the dusty cloud, the protostar begins to shine faintly in infrared light. To human eyes, it would still be completely hidden by the thick layers of gas and dust surrounding it. But infrared telescopes can see through those layers, through their instruments. Astronomers observe the faint warmth of these newborn objects scattered throughout molecular clouds. Each one is a star in the earliest stage of its life, and the environment around a protostar is far from simple. As the gas falls inward, it rarely drops straight toward the center. The collapsing cloud almost always contains some slight motion, a gentle spin that was already present in the gas before the collapse began. That small rotation becomes important, because as the cloud shrinks, the rotation speeds up. The same effect happens when a spinning ice skater pulls their arms inward. The spin becomes faster as the body becomes more compact. Inside a collapsing core, the same physical rule applies. The gas begins to spin more rapidly as it falls inward, and instead of plunging directly into the center, much of the material spreads out into a rotating disk surrounding the protostar. This structure is known as a protoplanetary disk. If you could see one clearly, it would look like a flattened ring of gas and dust swirling gently around the newborn star. These disks can extend for billions of kilometers. In many cases, they are larger than the entire orbit of Neptune in our own solar system. Within the disk, gas and dust continue drifting inward toward the protostar. Some of the material gradually falls onto the young star, helping it grow more massive. But not all of the material follows that path. Much of the dust remains suspended in the disk itself, and this dust is not insignificant. The particles are incredibly small, often no larger than grains of smoke or microscopic fragments of rock. Yet these tiny grains play a remarkable role in the future of planetary systems. Dust grains provide surfaces where atoms and molecules can gather. They can stick together when they collide. They can accumulate slowly over time. In the calm environment of the disk, these tiny grains begin bumping into one another again and again. Most collisions are gentle. Particles cling together through faint electrical forces. Small clumps form. Those clumps collide with other clumps, and gradually, almost unimaginably slowly, the first building blocks of planets begin to appear. At this stage, they are still extremely small, pebble-sized objects drifting through a disk of gas and dust. But over millions of years, these particles can continue growing, eventually forming asteroids, comets, and the solid cores of planets. It's a quiet beginning. The future architecture of entire solar systems starts with collisions between grains too small to see, and while this slow gathering unfolds within the disk, the young protostar itself continues changing. More gas falls inward. The central temperature rises. The pressure inside the protostar grows stronger. Eventually, deep in the center, the conditions approach something extraordinary. The temperature climbs toward millions of degrees. The pressure becomes immense, and the hydrogen atoms inside the core begin moving fast enough to collide in a very different way. Instead of simply bouncing apart, some of those hydrogen nuclei begin to fuse together. This process is nuclear fusion. It releases tremendous energy, far more energy than ordinary chemical reactions. Fusion is the process that powers every star in the universe, including our own sun. But in the early protostar stage, fusion has not yet fully stabilized. The star is still gathering material, still adjusting, still surrounded by its thick cocoon of gas and dust. At the same time, the protostar begins producing powerful outflows. Jets of gas shoot outward from the poles of the star, streaming into the surrounding cloud. These jets can travel for enormous distances, carving narrow tunnels through the gas. Astronomers often detect these jets as glowing streaks emerging from young stellar objects. The effect is almost like a pressure valve. As the protostar gathers material through the disk, it also releases energy and gas outward through these narrow jets. Over time, these outflows begin clearing away some of the surrounding cloud. The once hidden star slowly begins to reveal itself. Light from the growing star spreads into the surrounding nebula. Dust particles scatter that light, creating faint glowing patches within the cloud. And what was once a quiet, dark, molecular cloud slowly becomes something else. A stellar nursery, a region where young stars illuminate the gas that helped create them. And somewhere inside that glowing cloud, a small rotating disk continues its slow work. Tiny dust grains drifting together, pebbles forming, the earliest hints of planets beginning to appear. The process is still incredibly young, but the stage is now set, because as more young stars ignite inside the nebula, they begin to transform the cloud itself. Their light spreads outward, their winds push against the surrounding gas, and the once dark nursery begins to glow from within. As more young stars begin to shine inside the cloud, the entire nursery slowly changes its appearance. What was once a dark, quiet region of cold gas begins to fill with light. This transformation happens gradually. At first, the glow is faint, small pockets of warmth spreading through the surrounding gas. But as additional stars ignite, their combined energy begins illuminating the nebula more clearly. Young stars, especially the larger and hotter ones, release strong radiation into their surroundings. Among the most important forms of this radiation is ultraviolet light. Unlike the softer visible light we see with our eyes, ultraviolet light carries enough energy to change the atoms it encounters. When ultraviolet radiation passes through hydrogen gas, it can knock electrons away from the hydrogen atoms. This process is called ionization. The gas becomes ionized hydrogen, and when those free electrons eventually recombine with the hydrogen atoms again, the atoms release energy in the form of light. Often that light appears as a soft reddish glow. This is why many famous nebula photographs show vast red clouds drifting through space. The color is not paint or dust. It is the visible glow of energized hydrogen gas responding to the radiation from nearby stars. Astronomers call these glowing regions H2 regions, a name that simply means ionized hydrogen inside them. The cloud that once seemed invisible now shines with a gentle internal light. It's easy to imagine these glowing nebulae as calm and still, but in reality, they are dynamic environments, constantly being shaped by the young stars inside them. Those stars do more than shine. They also breathe, Young stars release steady streams of charged particles known as stellar winds. These winds flow outward from the star at tremendous speeds, carrying energy into the surrounding gas. Over time, these winds push against the nebula like a slow cosmic breeze. Gas is swept outward. Dust is displaced. The once smooth cloud begins developing cavities and arches. Imagine a gentle wind moving through a thick morning fog. The fog doesn't disappear instantly, but it begins forming patterns, tunnels, openings, and soft curved shapes where the air has moved through. Something similar happens inside stellar nurseries. The winds from newborn stars carve hollow spaces into the cloud. Surrounding gas piles up at the edges of these expanding bubbles, forming glowing shells that slowly expand through the nebula. In some places, the radiation from stars eats away at the edges of denser clumps of gas. These clumps resist erosion longer than the surrounding material. As the outer gas is gradually removed, the denser regions remain behind as tall columns of shadowy material. Astronomers sometimes call these structures pillars. One of the most famous examples lies inside the Eagle Nebula, towering shapes known as the pillars of creation. In telescope images, they appear as immense columns of gas stretching across light years of space. Yet even these structures are temporary. Radiation and stellar winds slowly wear them down over time. Gas evaporates from their surfaces. Dust drifts away. What looks like a stable cosmic monument is actually part of a slow, ongoing transformation. And inside the darker tips of some pillars, the process of star formation can continue. Dense pockets of gas hidden within the pillars may still collapse under gravity, forming new protostars sheltered briefly from the surrounding radiation. So even while one generation of stars reshapes the nebula, another generation may quietly begin inside its shadowed corners. It's a remarkable balance, light and gravity working together, sometimes competing, sometimes cooperating, shaping the cloud in different ways. But the story of a stellar nursery does not involve only one star forming at a time. More often, stars appear together. In many nebulae, dozens or even hundreds of protostars begin forming within the same cloud. These stars share a common origin. They were born from the same reservoir of gas, collapsing in nearby regions of the molecular cloud. As they emerge from the cloud, they form what astronomers call a star cluster. If you could watch this process unfold over millions of years, you would see a once dark nebula gradually filling with a small constellation of young stars. At first, their light remains partially hidden behind dust, but as stellar winds continue clearing away the cloud, the stars become easier to see. The cluster begins to sparkle inside the thinning gas. Each star follows its own path of development. Some are small and relatively cool. Others grow massive and brilliant, radiating enormous amounts of energy into the surrounding space. Yet, despite their differences, they all share the same birthplace, a quiet cloud that once drifted silently between the stars. And over time, the nebula that formed them continues to fade. Gas disperses into the wider galaxy. Dust spreads outward. The stellar nursery gradually dissolves. What remains is a young star cluster, a group of newly formed suns shining together as they drift slowly through the galaxy. Our own sun may once have been part of such a cluster, Astronomers suspect that thousands of sibling stars may have formed alongside it in the same nebula billions of years ago. Over time, gravitational interactions scattered those stars across the Milky Way. Today, they are almost impossible to identify with certainty, but somewhere in the galaxy, a few of them may still be shining. Stars that were born in the same cloud as our sun, long before Earth existed. And while some stellar nurseries fade away after forming a cluster, the galaxy continues producing new ones elsewhere. Across the spiral arms of the Milky Way, vast molecular clouds still drift quietly through space. Inside them, gravity is gathering gas into new dense cores. Protostars are forming, disks are spinning, young stars are beginning to glow. The same gentle process continues, repeating itself across enormous distances. And if we move a little farther outward now, beyond the cloud itself, we begin to see how entire galaxies help guide where these nurseries appear. If we could slowly rise above one of these stellar nurseries and look outward across the galaxy, we would notice something interesting. Star formation does not happen randomly everywhere. Instead, it tends to appear in certain regions more often than others. In galaxies like our Milky Way, many of these regions lie along the graceful curves known as spiral arms. From a distance, spiral galaxies look almost like enormous pinwheels made of stars. Long, luminous arms wind outward from the center, sweeping gently through space. These arms are not solid structures. They are more like slow-moving waves that travel through the galaxy's disk. As clouds of gas drift through the galaxy, they pass through these waves. And when they do, the gas becomes slightly compressed. The compression is subtle, but it matters. A cloud that was drifting peacefully through space may suddenly find itself squeezed just enough that gravity begins gathering its material more effectively. The gas thickens, the cloud cools further, and inside that denser environment, new molecular clouds begin forming. In this way, spiral arms often become long chains of stellar nurseries. If you could see the Milky Way from far outside, you might notice glowing regions scattered along its arms, bright patches where new stars are forming inside vast nebulae. Some of these regions shine brilliantly with ionized gas, illuminated by hot young stars. Others remain dark and hidden, their star formation still buried inside cold molecular clouds, but together they form a kind of quiet pattern across the galaxy. The spiral arms help guide where gas gathers and where stars are more likely to appear. In a sense, the structure of the galaxy gently influences the birthplaces of its stars, and one of the most beautiful examples of a nearby stellar nursery lies not far from our own position in the Milky Way. It appears in the constellation Orion. On a clear winter night, Orion is easy to recognize. 3 bright stars form a straight line across the sky, known as Orion's belt. Just below them lies a faint glowing patch that can sometimes be seen even with the naked eye. That glow comes from the Orion Nebula. The Orion Nebula is one of the closest large star-forming regions to Earth, located about 1,300 light-years away. Because it is relatively nearby, astronomers have been able to study it in extraordinary detail. Inside this glowing cloud, hundreds of young stars are forming at the same time. Many of them are still extremely young in cosmic terms, perhaps only a few 100,000 years old. Compared with the sun, which is more than 4 billion years old. These stars are just beginning their lives. Infrared telescopes have revealed that many of these young stars are surrounded by protoplanetary disks, the same kind of spinning disks of gas and dust that once surrounded our own young sun. In some telescope images, these disks appear as tiny, dark silhouettes against the glowing background of the nebula. Each one is a potential solar system in the making. Inside those disks, dust grains are drifting together. Small particles collide. Clumps slowly grow larger. Given enough time, some of these disks may produce planets, moons, asteroids, and comets. In other words, the Orion Nebula is not only forming stars, it is very likely forming future planetary systems as well, perhaps somewhere inside that glowing cloud. A rocky world will one day circle a distant sun. Perhaps oceans will form there. Perhaps skies will appear over landscapes shaped by gravity and chemistry. Or perhaps those systems will remain quiet and uninhabited. The universe does not hurry these possibilities. It simply provides the conditions. Gravity gathers the gas, disks spin, particles collide, and the slow architecture of solar systems begins to take shape. Meanwhile, the young stars inside the Orion Nebula are already transforming their environment. Some of the largest stars in the region shine with extraordinary intensity. Their ultraviolet radiation floods the surrounding cloud, ionizing the gas and causing the nebula to glow brightly. At the same time, stellar winds stream outward from those stars, pushing against the surrounding material. Gas begins drifting away from the cluster. The cloud slowly erodes. Over the course of a few million years, much of the original nebula will likely disperse into the wider galaxy. The stars that formed inside it will remain behind, shining together as a loose cluster before gradually drifting apart. And while this transformation unfolds in Orion, similar scenes are taking place elsewhere across the spiral arms of the Milky Way. New clouds are gathering, new clusters are forming, young stars are lighting their surrounding nebulae. From the perspective of a single human lifetime, the galaxy appears almost motionless. But if we could watch it across millions of years, we would see star-forming regions appearing and fading like slow pulses of light across the spiral arms. And the forces shaping these nurseries do not always come from within the cloud itself. Sometimes they arrive from far more dramatic events that send powerful waves of energy through interstellar space, quietly preparing the conditions for the next generation of stars. And those events often begin with the explosive end of a massive star. Sometimes the quiet beginnings of new stars are connected to events that seem, at first, much more dramatic. The universe has a long memory, and occasionally, the death of one star can help begin the life of many others. Massive stars, the kind that shine with enormous brightness in young clusters, live very different lives from stars like our sun. They burn their fuel much more quickly, using up the hydrogen in their cores at a tremendous rate. While our sun is expected to live for around 10 billion years, some of these massive stars survive for only a few million. In cosmic terms, that is a very short life, but during that short time, they release extraordinary amounts of energy into their surroundings. Their light floods the nearby nebula. Their stellar winds push vast shells of gas outward through the cloud, and eventually, when the fuel in their cores begins to run out, their story can end in one of the most powerful events in the universe, a supernova. In a supernova explosion, the star's outer layers are hurled outward into space at incredible speeds. A brilliant flash of light briefly outshines entire galaxies, and shock waves ripple outward through the surrounding interstellar gas. From nearby, the event would be overwhelming, but from the broader perspective of the galaxy, something quieter begins to follow. The expanding shock wave from the supernova travels outward through space, spreading into nearby clouds of gas and dust. When that wave encounters a molecular cloud, it can compress parts of the cloud as it passes through. Gas that once drifted loosely together becomes squeezed into denser regions. And in some of those regions, gravity begins gathering matter more strongly than before. In this way, the explosion of a dying star can sometimes trigger new star formation in a neighboring cloud. The process is still slow. The shock wave may only slightly increase the density of the gas, but that small change can be enough to begin the formation of new dense cores. Once again, gravity takes over. Molecules drift inward. The gas cools. New protostars begin forming. It is a quiet chain reaction, stretching across vast distances. Astronomers have observed evidence of this kind of triggered star formation in several nebulae. Shells of expanding gas appear to be pushing into nearby molecular clouds, where new clusters of young stars are beginning to emerge. Some scientists even suspect that something similar may have helped begin the formation of our own solar system. Inside certain meteorites found on Earth, researchers have discovered traces of radioactive elements that must have formed inside a nearby supernova long ago. These elements decay quickly on cosmic timescales, which suggests that the explosion happened not long before the material that formed our solar system condensed. One possible explanation is that a nearby supernova both enriched the cloud with new elements and compressed the gas enough to help begin the collapse that formed our sun. If that idea is correct, then the birth of our solar system may have been quietly linked to the death of another star. The debris from that ancient explosion would have mixed into the gas of the nebula. Atoms forged in the heart of the dying star would have become part of the cloud that later formed the sun, the planets, and everything that now exists here on Earth. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it once drifted through clouds like these. It's easy to miss how strange that really is. Matter travels through enormous cycles in the galaxy. Stars form from gas. Stars live and shine for millions or billions of years. Some eventually return their material back to space, scattering it across interstellar clouds. And from those enriched clouds, new stars begin again. Astronomers sometimes describe this as a kind of cosmic recycling. Gas flows through galaxies in slow loops of creation and transformation. Nebulae gather material. Stars ignite, and eventually, that material returns to space to help form the next generation. The galaxy is not a static collection of stars. It behaves more like a vast ecosystem of matter and energy, where the ingredients for new suns are constantly being prepared. Inside molecular clouds scattered throughout the Milky Way, the process continues quietly. Cold gas drifts through dark regions of space. Gravity gathers small pockets of matter, Protostars glow faintly within their dusty cocoons. Disks spin around young stars, where tiny dust grains collide again and again. And over millions of years, entire star clusters slowly emerge from these quiet environments. Some of those stars will shine for billions of years. Others will live quickly and end dramatically, scattering their material across the galaxy once more. And through all of these cycles, nebulae remain the quiet starting point, the places where the next generation of stars begins. If we could watch the Milky Way over immense stretches of time, we would see these stellar nurseries appearing and fading across its spiral arms, clouds gathering, clusters igniting, gas dispersing, and new nebulae forming again somewhere else in the galaxy. But to truly understand how long this process has been unfolding, we have to widen our perspective even further, because star-forming clouds like these did not exist in the very earliest moments of the universe. There was a time when the cosmos contained no stars at all, no nebulae, no galaxies, just a vast expanding ocean of hydrogen and helium drifting through space. And from that simple beginning, the very first stellar nurseries slowly began to appear, long before the Milky Way existed. Before the spiral arms slowly took their shape, the universe was a much simpler place. There were no nebulae yet, no star clusters glowing inside cold clouds, no galaxies drifting through space. Instead, the cosmos was filled almost entirely with two very simple elements: hydrogen and helium. These elements formed in the earliest moments after the universe began expanding. As the young universe cooled, these atoms spread through space in a vast, thin sea of gas. For a long time, nothing else existed. There were no stars to shine, no planets to form, no heavy elements like carbon, oxygen, iron, or calcium. Just hydrogen and helium drifting quietly through the expanding universe. But even in that early simplicity, the same patient force that shapes nebulae today was already at work: gravity. Wherever the gas was slightly denser, gravity pulled more material toward it. Very slowly, tiny fluctuations in density began to grow larger. Over millions of years, then tens of millions. The gas gathered into larger and larger regions. Eventually, these regions became the first proto-galaxies, the earliest structures where matter had collected in significant amounts. Inside those young galaxies, the gas continued cooling and condensing, and just as it does today inside nebulae, gravity began gathering parts of the gas into dense pockets. The first stellar nurseries were beginning to appear, but these early nurseries were very different from the nebulae we see in the modern universe. They lacked many of the ingredients we are familiar with today. There was almost no dust, no complex molecules, no heavy elements, only hydrogen and helium gas collapsing under gravity. Because of that simplicity, astronomers believe the very first stars may have been extremely massive, perhaps dozens or even hundreds of times heavier than our sun. Without heavier elements to help cool the gas, clouds may have collapsed into fewer but larger stars. These early stars would have shone with extraordinary brightness. Their intense radiation flooded the young universe with light for the first time. For hundreds of millions of years before this moment, the universe had been mostly dark. There were no luminous objects to illuminate the vast distances between galaxies. But when the first stars ignited, that darkness began to fade. Light spread outward across the cosmos. The earliest stellar nurseries had begun their work. Yet those first stars lived fast and short lives because they were so massive. They burned through their nuclear fuel quickly. Some may have survived only a few million years before reaching the end of their lives, and when they died, many of them exploded as powerful supernovae. Those explosions were transformative events. For the first time in cosmic history, heavy elements were forged inside the hearts of stars and scattered into space. Carbon, oxygen, silicon, iron. These elements were created during the violent final stages of stellar evolution and then flung outward across the surrounding gas. Over time, the debris from those explosions mixed with the surrounding clouds. The next generation of nebulae began forming from gas that now contained more than just hydrogen and helium. For the first time, dust grains could form. Complex molecules began appearing. The chemistry of the universe became richer, and this chemical enrichment changed the way star formation worked. Dust grains allowed gas clouds to cool more efficiently. Molecules formed more easily. Clouds could collapse into smaller fragments. Instead of forming only extremely massive stars, nebulae could now produce a wider variety of stellar sizes, including stars like our Sun. This gradual change unfolded across billions of years. Generation after generation of stars formed, lived, and died. Each generation enriched the galaxy with more heavy elements. Each generation helped shape the conditions for the next. By the time the Milky Way reached its present form, its interstellar clouds had become complex chemical environments, molecular clouds filled with hydrogen molecules, icy dust grains, and a wide range of organic compounds drifted through the spiral arms. Inside these clouds, the familiar process of star formation began repeating itself across the galaxy. Dense cores gathered, protostars formed, protoplanetary disks appeared. Planetary systems slowly assembled from swirling dust, and somewhere inside one of those clouds, about 4.6 billion years ago, a small yellow star began its own life. Our Sun, the cloud that formed our solar system, was likely just one of many stellar nurseries active in the Milky Way at that time. Within it, a dense core collapsed. A protostar warmed at the center. A disk of gas and dust spread outward. Tiny grains began colliding. Planets slowly gathered from those grains. The early solar system was born from exactly the same processes still unfolding in nebulae today. And that realization brings a certain quiet comfort. When we look up at the night sky and see glowing nebulae through telescopes, places like the Orion Nebula, the Carina Nebula, or the Lagoon Nebula, we are not just seeing distant clouds, we are seeing environments that once existed here, the same kinds of cosmic nurseries that gave rise to our own Sun. The galaxy continues forming stars in these places even now. Across enormous clouds of gas and dust, gravity continues gathering matter. Protostars continue glowing faintly in their dusty cocoons. Disks continue spinning. And somewhere, tiny grains of dust are colliding again and again, beginning the slow process that may one day form entirely new worlds. If we could watch the Milky Way over millions of years, we would see these stellar nurseries appearing and fading across its spiral arms like slow-moving constellations, clouds gathering, stars igniting, gas dispersing. then the cycle beginning again somewhere else in the galaxy. The universe rarely rushes. Its most important transformations often unfold through patience and time, and the quiet clouds drifting between the stars remain the places where the next generation of suns is already beginning to take shape. In the next part of our journey, we'll drift a little closer to the chemistry hidden inside these clouds, the delicate molecules and tiny dust grains that help guide the birth of stars and planets alike. Inside the quiet darkness of a molecular cloud, something delicate is happening. The gas drifting through these regions is not made of single atoms alone. Over time, many of those atoms combine into molecules, small structures where two or more atoms attach together and move through space as a unit. The most common of these is molecular hydrogen, formed when two hydrogen atoms join together. But molecular clouds contain more than just hydrogen. Astronomers studying these regions with sensitive radio telescopes have discovered a surprising variety of molecules drifting through the cold gas. Carbon monoxide is common, as are molecules containing oxygen, nitrogen, and other elements. Even more complex compounds have been detected. Simple organic molecules that include chains of carbon atoms. These discoveries can feel almost surprising at first. It's easy to imagine interstellar space as empty and lifeless. But inside these cold clouds, a quiet kind of chemistry is constantly taking place. The key to much of this chemistry lies in something extremely small: dust. Interstellar dust grains are tiny particles of solid material floating through the gas of the nebula. Many are made of silicates, minerals similar to those found in rocks on Earth. Others contain carbon-rich compounds. Most dust grains are incredibly small. Many measure only a fraction of a micrometer across, far smaller than the width of a human hair. Yet these tiny particles play an enormous role in the life of a nebula, because atoms drifting through space can stick to their surfaces. Imagine a grain of dust floating through a cold cloud. A hydrogen atom drifts nearby and briefly attaches to the grain's surface. Soon, another hydrogen atom arrives and settles beside it. On the surface of the grain, the two atoms meet. They combine. A molecule of hydrogen forms and then drifts away back into the cloud, without dust grains. Many of these molecular reactions would happen far less often. The grains act as quiet meeting places where atoms can gather and interact. Over millions of years, countless such reactions occur. Water molecules can form, carbon-based compounds assemble, thin, icy coatings may build up on the surfaces of dust grains as molecules freeze onto them in the deep cold of the cloud. In the densest regions of molecular clouds, astronomers believe many dust grains become coated in layers of ice made from water, carbon dioxide, ammonia, and other simple molecules. These icy mantles may only be a few hundred molecules thick, yet they carry the ingredients for later stages of planetary chemistry. When a dense core begins collapsing to form a protostar, these dust grains are swept inward along with the gas. They become part of the protoplanetary disk that forms around the young star. Inside that disk, the dust grains collide. At first, the collisions are extremely gentle. Tiny particles drifting through the disk bump into one another and cling together through weak electrical forces. Small clusters form. Those clusters collide with others. Over time, the clusters grow larger. pebble-sized fragments appear. Eventually, if the conditions are right, those fragments can continue accumulating material and grow into objects kilometers across. These early bodies are known as planetesimals. They are the first real building blocks of planets. Inside young planetary systems, countless planetesimals orbit the newborn star. Some collide and merge. Others shatter into smaller fragments. Through millions of years of collisions and accumulation, some of these bodies grow large enough that gravity begins shaping them into round planetary objects. This long process transforms dust grains into entire worlds, and the remarkable thing is that every step of it begins with particles so small they are almost impossible to see. It's easy to miss how subtle this beginning really is. When we imagine planets forming, we might picture dramatic collisions or fiery worlds taking shape, but the very first stage happens in quiet darkness. Dust grains drifting through a disk, tiny collisions happening again and again, slow accumulation, gravity waiting patiently as the pieces grow larger. Meanwhile, the young star at the center of the system continues evolving. As material falls onto the protostar, the temperature and pressure in its core continue rising. Eventually, the conditions become stable enough for nuclear fusion to begin in a sustained way. Hydrogen nuclei fuse together to form helium. This process releases tremendous energy. When fusion begins steadily, the protostar finally becomes a true star. The energy from fusion pushes outward against the inward pull of gravity, creating a balance that allows the star to shine steadily for millions or billions of years. At this point, the star begins entering what astronomers call the main sequence, the long, stable phase that most stars spend the majority of their lives in. But before that stability fully settles in, the young star continues interacting strongly with the surrounding disk. Jets of gas stream outward from the poles of the star, traveling along powerful magnetic fields. These jets can stretch for enormous distances, sometimes several light years long. Where the jets collide with the surrounding gas, they create small glowing shock waves known as Herbig-Haro objects, bright knots of gas visible in certain star-forming regions. These glowing streaks reveal the presence of very young stars still embedded in their birth clouds. Over time, the energetic activity of the star begins clearing away the disk and surrounding gas. Stellar winds blow outward. Radiation warms the remaining material. Gas gradually drifts away from the system. The thick cocoon of the stellar nursery slowly thins, and eventually, the young star emerges into clearer space. The disk that once surrounded it may still remain, gradually forming planets or smaller bodies. But the larger cloud that formed the star is slowly dispersing back into the galaxy. The stellar nursery fades. The newborn star now shines on its own. And far away, in other regions of the galaxy, new molecular clouds continue drifting quietly through the spiral arms. Inside them, the same tiny processes continue unfolding. Dust grains gathering molecules, gas cooling in shadowy regions, gravity gathering matter into dense cores. The first faint hints of future stars beginning to appear once again. And if we widen our perspective just a little further, we can begin to see how entire galaxies sustain this quiet process of star birth over billions of years. If we step back from a single nebula for a moment, the larger rhythm of the galaxy begins to appear. The Milky Way is not only a collection of stars drifting through space, it is also a vast reservoir of gas and dust, slowly circulating through the disk of the galaxy over immense stretches of time. Between the stars, enormous clouds drift quietly through the spiral arms. Some of those clouds remain thin and diffuse, barely gathering into anything substantial. Others cool and thicken, gradually becoming the molecular clouds where star formation can begin. In this way, the galaxy behaves almost like a slow ecosystem. Gas flows through different stages. A diffuse cloud becomes denser. A molecular cloud forms. Dense cores appear inside the cloud. Stars ignite. Then, over millions of years, radiation and stellar winds disperse the remaining gas back into the wider galaxy. Eventually, that gas drifts again through the spiral arms, where new molecular clouds may begin forming once more. The same atoms participate in this long cycle again and again. Hydrogen, that once drifted quietly between stars, may become part of a molecular cloud. That cloud may collapse into a protostar. The protostar may shine for billions of years before eventually releasing its material back into space. Nothing is wasted. Matter simply moves through different forms. Astronomers sometimes call this the recycling of the interstellar medium, the slow transformation of gas and dust as it flows through cycles of star birth and stellar evolution. And although the galaxy appears calm when we look up at the night sky, this process is unfolding constantly across enormous distances. New nebulae form. Young stars ignite. Older stars quietly age. Gas drifts back into the darkness between the stars, where gravity may one day gather it again. Some galaxies carry out this process slowly, producing new stars at a steady but modest pace. The Milky Way is one of these calmer galaxies, forming only a few new stars each year on average. That might sound like a lot, but across a galaxy containing hundreds of billions of stars, it is actually a fairly gentle rate of growth. Other galaxies are far more active. Astronomers call them starburst galaxies. Inside these galaxies, enormous amounts of gas have gathered into dense regions, sometimes triggered by collisions with neighboring galaxies. The result can be a sudden surge of star formation, where new stars appear far more rapidly than usual. In these environments, vast nebulae collapse into clusters of stars at a remarkable pace. Entire regions of the galaxy glow with intense light as young stars ignite in great numbers. Yet even in these energetic galaxies, the underlying physics remains the same. Cold gas gathers. Gravity pulls matter inward. Protostars form. Disks appear. And the quiet architecture of planetary systems begins once again. The scale may be larger. The pace may be faster. But the basic process remains beautifully simple. Gravity gathers matter. Pressure and temperature shape its collapse. Radiation from young stars slowly transforms the surrounding cloud. From these few physical principles, the galaxy builds extraordinary complexity. Star clusters, solar systems, planets, and eventually, in some rare places, environments where life can appear. But all of that complexity traces its origins back to something very gentle. A cold cloud drifting through space, hydrogen atoms moving slowly through darkness, dust grains floating quietly among them. The earliest stages of star formation do not announce themselves with bright light or violent motion. They begin almost invisibly, a slight thickening of the gas, a tiny region becoming just a little denser than the surrounding cloud, gravity beginning its patient work. From inside the system, it would be nearly impossible to notice anything changing at all. Yet, across millions of years, that quiet gathering becomes something remarkable. A protostar glows, a disk forms, planets begin assembling from dust, and eventually, a new star emerges into the galaxy, joining the countless others that shine across the spiral arms. If we could watch the Milky Way over hundreds of millions of years, the galaxy would appear alive with these slow transformations. Nebulae appearing like faint blossoms in the darkness, clusters of stars igniting inside them, clouds dispersing and fading, then new clouds gathering somewhere else. The entire galaxy, breathing in a rhythm that is far too slow for human lifetimes to notice. And yet the evidence of this process surrounds us. Every bright young star in the night sky was once hidden inside a cloud like these. Every planet orbiting those stars began as dust drifting through a disk around a newborn sun. And even now, across the vast distances of the Milky Way, new stellar nurseries continue their quiet work. Gravity gathers the gas. Molecules drift together. Dust grains collide softly inside spinning disks. The next generation of stars begins forming in darkness. And while those distant nurseries continue their slow transformations, the stars they produce will eventually carry their own stories forward through the galaxy. Some will shine steadily for billions of years. Others will live quickly and end in brilliant explosions. And through all of these different paths, the matter that once drifted through nebulae will continue traveling through the cosmic cycles of creation and change. The clouds between the stars may appear calm and empty at first glance, but they remain some of the most important places in the entire universe, because they are where the next suns are quietly beginning. And somewhere inside one of those drifting clouds, the process is beginning again. A region of gas grows just slightly thicker than the surrounding space. Nothing dramatic happens at first. The change is almost impossible to detect. But gravity notices. In the quiet interior of a molecular cloud, gravity begins its slow and patient work once more, pulling nearby gas inward toward that slightly denser region. Atoms drift closer. Molecules follow. The cloud that once seemed perfectly uniform develops subtle knots and pockets where the gas becomes thicker. These pockets do not appear suddenly. They form over immense stretches of time. Tens of thousands of years pass, then hundreds of thousands. Inside the cloud, the gas grows denser still. Eventually, these regions become what astronomers call dense cores. A dense core is still part of the larger cloud, but within it, the material has gathered enough that gravity is beginning to take control of its future. The inward pull of gravity grows stronger than the outward pressure of the surrounding gas, and once that balance tips, the collapse begins. The motion is still extremely gentle. Gas drifts slowly toward the center of the core, almost like mist settling into a hollow. Yet even this slow inward movement carries enormous consequences. As more material gathers at the center, the density increases. The temperature begins to rise. The core becomes more compact. Deep inside the cloud, a new protostar is beginning to take shape. This process can occur many times within the same molecular cloud. In fact, the largest clouds often produce entire groups of stars at once. the cloud fragments into multiple dense cores, each collapsing independently, each forming its own young star. Over time, these stars emerge as small clusters, stellar families born from the same parent cloud. At first, the stars remain hidden inside the gas and dust that formed them. The thick material surrounding the young protostars blocks visible light, making them difficult to observe with ordinary telescopes. But astronomers have learned to look for them in other ways. Infrared telescopes can detect the faint warmth of the protostars glowing through their dusty envelopes. Radio telescopes can observe the molecular gas itself, revealing the hidden structures inside the cloud. Through these instruments, scientists have discovered thousands of young stellar objects scattered across the Milky Way. Each one marks a star in the earliest stages of its life. And in many of these systems, the familiar pattern appears again. A protostar at the center, a rotating disk surrounding it, jets of gas streaming outward along magnetic fields. These jets can extend across enormous distances, sometimes several light years from the star itself. Where they collide with the surrounding gas, they create glowing shock waves that appear as bright knots in astronomical images. These structures are known as Herbig-Haro objects. They are signs of a very young star still interacting strongly with the gas that formed it. The jets act like narrow streams of energy escaping from the system, carrying away some of the angular momentum of the rotating disk. Without this release of energy, the gas might not be able to fall inward as efficiently. In a sense, the star is balancing its growth. Material spirals inward through the disk toward the protostar. At the same time, jets carry energy outward into the surrounding cloud. This delicate balance allows the young star to continue gathering mass while slowly shaping its environment. Meanwhile, inside the disk, the tiny dust grains continue their quiet work. Collisions occur again and again. Small grains stick together. Larger fragments begin to form. Pebbles gather into clusters. Clusters grow into objects large enough that their own gravity begins pulling in additional material. Over millions of years, some of these objects grow into planetesimals, the building blocks of planets. Inside a young solar system, countless planetesimals may orbit the newborn star, gradually colliding and merging. Some of these collisions build larger bodies. Others shatter objects into smaller fragments. The environment is busy, but still slow compared with human timescales. Even the formation of a single planet can take tens of millions of years. Yet all of it begins with something incredibly small. Dust grains drifting through a disk of gas. It's easy to miss how quiet this beginning really is. The universe does not assemble worlds through sudden acts of creation. Instead, it gathers them patiently. Particles meet, clumps grow. Gravity gently pulls matter into new forms, and over time, entire planetary systems emerge from these subtle beginnings. Eventually, the young star itself begins to stabilize. Deep inside its core, nuclear fusion ignites in a sustained and balanced way. Hydrogen atoms fuse together to form helium, releasing tremendous energy. The outward pressure from this energy balances the inward pull of gravity. The star settles into a stable phase of life. Astronomers call this the main sequence, the long period during which a star shines steadily, powered by fusion in its core. Our own sun is currently in this stage, and it has been for billions of years. But In the early stages of a stellar nursery, many stars are still younger than this. They are still gathering material, still clearing their surrounding disks, still interacting with the cloud that gave them birth. Over time, however, the environment around them continues changing. Radiation from the young stars heats the surrounding gas. Stellar winds push against the remaining material. The once dense nebula begins to thin. Gradually, the gas disperses into the wider galaxy. The stellar nursery fades. The stars remain, and what was once a quiet cloud of gas becomes a small constellation of newborn suns drifting slowly through space. Some of those stars may eventually form planetary systems. Some may remain solitary. A few may grow massive enough to live short, brilliant lives before ending in supernova explosions. But regardless of their individual futures, they all share the same origin: a cold cloud of gas and dust, a molecular nebula drifting quietly through the spiral arms of the galaxy. And somewhere else in the Milky Way tonight, far beyond our own skies, another cloud like that is already beginning. The same slow transformation. Gas is gathering. Dense cores are forming. Protostars are glowing faintly within their dusty cocoons. And the next generation of stars is quietly on its way. And while these young stars begin settling into their long lives, the cloud that formed them continues to change. A stellar nursery is never permanent. The same energy that allows stars to shine also begins clearing away the environment that created them. Radiation from the stars spreads through the remaining gas. Stellar winds push outward in slow, expanding waves. Over time, the once thick cloud begins to grow thinner. At first, this change is subtle. Small gaps appear in the surrounding gas. Cavities open where winds have pushed material outward. Light from the young stars begins to travel farther through the nebula than it could before. Gradually, the stars become easier to see. Astronomers observing star-forming regions often notice this stage as a transition. The bright glow of ionized gas still surrounds the cluster, but the dark molecular cloud that once hid the stars begins to dissolve. Gas streams outward from the region, drifting back into the wider galaxy. Dust grains spread apart. The nursery slowly fades. This process may take several million years, which in human terms is unimaginably long. Yet in the life of a star, it is only a brief beginning. Eventually, the cloud disperses almost completely. The young stars remain behind, now shining in relatively clear space. Without the thick surrounding gas, their light can travel freely across the galaxy. What remains is a young open star cluster. These clusters are groups of stars that formed together from the same molecular cloud because they share a common origin. The stars inside a cluster often have similar ages and chemical compositions. If you could observe one of these clusters up close, you might see dozens or hundreds of stars scattered loosely through space, drifting slowly together through the spiral arm of the galaxy. At first, gravity helps hold the cluster loosely together, but over time, the cluster gradually spreads apart. The galaxy itself is not perfectly still. Stars move through its gravitational field, orbiting the galactic center over hundreds of millions of years. As they travel, small gravitational interactions with other stars and clouds slowly alter their paths. Little by little, the cluster begins to disperse. Stars drift away from one another. The group that once formed together becomes more widely scattered. After tens or hundreds of millions of years, the original cluster may no longer be recognizable at all. The stars continue their journeys around the galaxy independently. Some may pass through spiral arms again. Others may travel through quieter regions between the arms, but the memory of their shared birthplace remains hidden in their chemistry. Astronomers sometimes study the chemical fingerprints of stars, the specific mixture of elements contained within them, to identify stars that may have formed from the same cloud long ago. In this way, researchers can sometimes trace ancient stellar families that were born together billions of years ago, but are now scattered across the Milky Way. It is a reminder that even though stars drift apart, their origins remain connected. Our own sun may once have been part of such a cluster. When the solar system first formed, the sun likely had thousands of nearby sibling stars shining within the same stellar nursery. Over the next hundreds of millions of years, gravitational interactions slowly scattered those stars across the galaxy. Today they are likely far away, perhaps on opposite sides of the Milky Way, yet they were born from the same cloud of gas and dust. Somewhere in the galaxy tonight, a few of them may still be shining quietly, ancient siblings of our sun that share the same cosmic birthplace. Meanwhile, the gas that once formed the solar system did not disappear. Much of it returned to the interstellar medium, the vast reservoir of gas and dust between the stars. Over time, that material may have drifted through spiral arms again, cooling and gathering into new molecular clouds. Inside those clouds, gravity may have begun forming new stars once more. The same atoms that helped form our sun may now be part of entirely different stellar systems. This long circulation of matter is one of the most remarkable features of galaxies. Atoms travel through different stages of cosmic history. They drift through interstellar clouds. They collapse into stars. They become part of planets, moons, or asteroids. Eventually, they return to space again through stellar winds or explosions. Then the cycle begins again. When we look up at the night sky, it can be easy to imagine that the stars are fixed and permanent. But the galaxy is constantly evolving. New stars are forming. Old stars are aging. Clouds of gas are drifting and gathering in new ways. Across billions of years, the Milky Way slowly reshapes itself through these cycles of birth and transformation. And the quiet clouds drifting between the stars remain the starting point for all of it. Because inside those clouds, gravity continues its patient work. Molecules gather, dust grains drift together, dense cores form inside the darkness. Protostars begin glowing faintly within their dusty envelopes. The next generation of stars is already taking shape, and far beyond our own sky tonight, in regions of the galaxy we will never see with our eyes, those stellar nurseries continue their quiet work, building new suns from the simplest ingredients in the universe. And even after a stellar nursery has faded, its influence does not disappear from the galaxy. The stars that emerged from the cloud continue carrying the story of their birth with them. Each star contains the chemical memory of the nebula that formed it. The gas that collapsed into the star's core brought along traces of elements that had been scattered through the galaxy by earlier generations of stars: carbon, oxygen, silicon, iron. These elements were not present in the earliest universe. They were created inside stars and later released into space through stellar winds and supernova explosions. When those elements mixed with cold molecular clouds, they became part of the next cycle of star formation. Over billions of years, this slow enrichment has changed the chemistry of the galaxy. The earliest stars formed almost entirely from hydrogen and helium. But modern stellar nurseries contain far more complex mixtures of material. Dust grains rich in carbon drift through molecular clouds. Tiny crystals of silicate minerals float alongside them. Ices made of water and other molecules coat many of these particles in the deepest, coldest regions of the cloud. All of this material becomes part of the next generation of stars and planetary systems. In that sense, each star carries the legacy of many others that lived long before it. The atoms that make up a young star today may have passed through several earlier stars across cosmic history. They may have spent millions of years drifting through the galaxy before being gathered once again by gravity inside a new nebula. The galaxy slowly builds complexity through these cycles. At first, the universe contained only simple elements. Then stars began forging heavier ones. Those elements spread through space, enriching the clouds that later formed new stars. Eventually, those clouds produced planetary systems rich with chemical diversity. And somewhere within a few of those systems, conditions eventually allowed life to appear. All of that complexity began with something very quiet, cold gas drifting through darkness. It is easy to imagine the universe as a place defined by its most dramatic moments: exploding stars, black holes, brilliant bursts of energy. But much of its most important work happens quietly, in the calm interior of a molecular cloud, inside regions so cold and dark that even nearby starlight struggles to enter. There, atoms drift gently through space. Gravity slowly gathers them. Dust grains carry delicate chemical reactions on their surfaces. Dense cores form. Protostars glow faintly within their dusty cocoons. And over immense stretches of time, entire solar systems begin assembling from those simple ingredients. If we could watch the Milky Way across tens of millions of years, the pattern would become clear. Nebulae would appear along the spiral arms like faint blossoms of gas. Clusters of young stars would ignite within them. Gradually, the clouds would thin and disperse. The clusters would drift apart. Then, new clouds would gather somewhere else in the galaxy, beginning the process again. The Milky Way is not frozen in time. It is slowly evolving. New stars are being born, even now, in regions of the galaxy far beyond the reach of our eyes. Inside those distant clouds, gravity is gathering atoms into new patterns. Dense cores are forming quietly in the darkness. Protostars are beginning to glow inside their dusty envelopes. Around those protostars, disks of gas and dust are spinning gently. Inside those disks, microscopic grains are colliding, sticking together, and beginning the slow process of planet formation. Some of those disks will eventually produce entire planetary systems. Others may disperse before planets can fully form. The outcomes vary, but the beginning is always similar. A quiet nebula drifting through space, a cold region where gravity slowly gathers matter, the earliest stage of a star beginning inside the darkness. And when you look up at the night sky tonight, many of the stars you see were once hidden inside such clouds. Long before they shone across the galaxy, they were simply parts of drifting nebulae, regions where gas and dust slowly gathered under gravity's patient pull. Some of those stars formed billions of years ago. Others may be only a few million years old. And somewhere in the Milky Way tonight, new stars are still beginning their lives inside clouds that remain invisible to our eyes. The galaxy continues quietly building its future suns, one nebula at a time. And when we look at these quiet, star-forming regions today, we are seeing only a brief moment within a much longer story. A nebula may spend millions of years drifting through the galaxy before star formation even begins. During that time, the cloud remains cold and dark, slowly gathering molecules and dust grains while gravity gently rearranges the gas. Then, once the first dense cores appear, the process of star formation may unfold across only a few million years. A short chapter compared with the billions of years many stars will eventually live. Afterward, the nursery disperses. The young stars drift outward into the galaxy, and the cloud that once held them together fades back into the wider sea of interstellar gas. In a sense, nebulae are temporary environments. They are places where the ingredients of stars briefly gather before spreading out again. Yet despite their temporary nature, these clouds are among the most important structures in the entire galaxy. Without them, stars could not form, planets could not assemble, solar systems would never appear. Every star we see began inside a cloud like this. Even the most distant stars in other galaxies were once part of similar nebulae, and this quiet pattern repeats itself everywhere. Astronomers observing other galaxies often see glowing star-forming regions scattered across their spiral arms or clustered within irregular clouds of gas. In some galaxies, these regions appear as bright knots of light where thousands of young stars have formed together. In others, the process unfolds more quietly, with small groups of stars emerging from faint molecular clouds. But regardless of the galaxy, the basic ingredients remain the same: cold gas, dust grains, gravity, time. From these simple elements, the universe constructs its stars, and from those stars come the energy and chemistry that shape entire planetary systems. The process may seem distant from our everyday lives, yet the connection is closer than it first appears. The atoms in our bodies were once part of the same cosmic cycles. Hydrogen atoms that drifted through ancient nebulae became part of stars. Inside those stars, nuclear fusion forged heavier elements. When those stars eventually returned their material to space, those elements became part of new clouds. From those clouds came new stars, new planets, and eventually, environments where chemistry could grow more complex. It's easy to miss how deeply connected we are to these quiet clouds drifting between the stars. The oxygen we breathe was forged in stellar interiors. The carbon in living cells was created in earlier generations of stars. The iron in our blood was once part of a star that ended its life in a supernova explosion. All of those atoms traveled through the galaxy long before becoming part of the Earth, and long before becoming part of us. When we imagine the universe, we often picture enormous distances and unfamiliar places. But the same processes unfolding in distant nebulae also shaped the history of our own solar system. 4.5 billion years ago, the sun formed inside a cloud, very much like the ones astronomers observe today. A molecular cloud drifted through the Milky Way. Gravity gathered a dense core. A protostar ignited at its center. a disk of gas and dust spun outward. Inside that disk, grains collided and slowly assembled into the early building blocks of planets. Over time, those fragments formed the worlds we now know: Mercury, Venus, Earth, Mars, and the distant planets beyond. The entire solar system grew from a cloud that once drifted quietly through space, and in that sense, every nebula we see through a telescope is also a glimpse into the distant past of our own star. When astronomers study places like the Orion Nebula or the Carina Nebula, they are not only observing distant clouds, they are witnessing processes that once happened here. They are watching the early chapters of solar systems being written. Somewhere inside those glowing clouds, tiny disks of dust are circling young stars. Inside those disks, particles are slowly gathering. Over millions of years, some of those systems may form planets, perhaps rocky worlds, perhaps gas giants, perhaps moons orbiting distant planets. Most of those systems will remain forever unknown to us, but the quiet process that forms them continues all the same. The galaxy does not pause. New clouds gather, new stars ignite, new solar systems begin their long evolution, and far beyond the reach of our telescopes tonight, there are likely countless young stars still hidden inside their dusty birth clouds. Their light has not yet escaped the thick layers of gas around them. Their planetary systems have not yet taken shape, but the process is already underway. Gravity is gathering matter. Molecules are drifting together. Dust grains are colliding softly inside rotating disks. The earliest architecture of future worlds is slowly being assembled, and this quiet work has been unfolding across the universe for billions of years. Long before the Earth existed, long before the sun began shining, long before our galaxy reached its present form, the universe has been building stars from drifting clouds of gas and dust, patiently, quietly, one nebula at a time. And even now, in the deep darkness between the stars, the next generation of suns is already beginning to form. And if we pause for a moment and imagine the Milky Way not as it appears tonight, but as it might look across millions of years, a slow pattern begins to emerge. The galaxy is not still. It moves with extraordinary patience. Gas drifts through the spiral arms like faint rivers of mist. Some regions remain thin and quiet, while others gradually thicken into the cold molecular clouds where star formation can begin. These clouds do not stay in one place forever. As the galaxy slowly rotates, the clouds travel along enormous paths around its center. A single orbit around the Milky Way can take more than 200 million years. During that time, a cloud may pass through spiral arms several times. Each passage gently compresses the gas, encouraging new regions of star formation to appear. Dense cores form. Protostars ignite. Stellar nurseries briefly glow within the dark clouds. Then, slowly, the clouds disperse. The young stars remain behind as loose clusters drifting through space, and the gas continues its journey. Some of it will gather again in another part of the galaxy, forming a new nebula. Some will become part of the winds flowing from aging stars. Some may eventually return to space through the quiet shedding of material from red giant stars. In this way, matter travels continuously through the galaxy. Atoms that once belonged to one star may drift through interstellar space for millions of years, before becoming part of another. They may spend time frozen onto dust grains in a molecular cloud. Later, they may be heated inside the core of a star, where nuclear fusion transforms them into heavier elements. Eventually, those elements may be scattered back into space again. Over billions of years, the same atoms participate in many different stages of cosmic history. Some astronomers like to think of galaxies as long-lived ecosystems of matter and energy. Gas flows through clouds. Clouds form stars. Stars return gas to space, and the cycle continues. But even within this cycle, there is remarkable variety. Some stellar nurseries produce small stars like our sun, quiet objects that will shine steadily for billions of years. Others produce massive stars that burn fiercely and live only short lives. Those massive stars can illuminate entire nebulae, carving vast cavities in the surrounding gas with their radiation and winds. Their lives are brief but powerful, and when they end, their supernova explosions scatter heavy elements across the galaxy, enriching future molecular clouds. Without those heavy elements, planets like Earth could never have formed. Rocks, metals, and complex chemistry all depend on the materials created inside stars long ago. So even the most dramatic stellar explosions ultimately help prepare the ingredients for new stellar nurseries. And this quiet preparation continues today. Across the Milky Way, astronomers estimate that the galaxy forms only a few new stars each year. That may seem like a small number for a galaxy containing hundreds of billions of stars, but star formation does not happen evenly. Instead, it occurs in scattered pockets across the spiral arms. Here a molecular cloud begins collapsing. There a cluster of young stars lights a glowing nebula. Elsewhere, an older cloud slowly disperses, its gas drifting outward once more. The pattern spreads across thousands of light years, and if we could observe the galaxy over immense stretches of time, we would see star-forming regions appearing and fading like slow waves of light across its disk, nebulae brightening as young stars ignite inside them, then fading again as the gas disperses, new clouds forming elsewhere, the galaxy gently renewing itself. In that sense, the Milky Way is never truly finished. It continues building new stars. It continues assembling new planetary systems. Some of those systems may remain cold and quiet. Others may one day develop complex chemistry on their planets, and in rare cases, perhaps something more. But all of those possibilities begin in the same quiet place, inside a cold, drifting cloud of gas and dust, a nebula. These clouds may seem faint and distant when we observe them through telescopes, yet they are among the most important environments in the universe, because they are where new stars begin, where solar systems slowly assemble, where the raw material of the cosmos gathers into new forms. And tonight, somewhere deep within the spiral arms of the Milky Way, gravity is already gathering atoms together inside another molecular cloud. Dense cores are forming in the darkness. Protostars are beginning to glow faintly inside their dusty envelopes. Disks of gas and dust are spinning slowly around those young stars. And inside those disks, tiny grains are colliding again and again, the earliest fragments of future worlds quietly taking shape. The galaxy does not hurry. It builds its stars with patience, cloud by cloud, nebula by nebula, across billions of years of quiet cosmic time. And if we could keep widening our view, rising slowly above the spiral arms and looking down on the Milky Way as a whole, the pattern would appear even clearer. Across the galaxy, star formation is never concentrated in only one place. Instead, it appears in scattered regions, quiet pockets where gas has gathered just enough for gravity to begin its slow work. Some of these pockets become the glowing nebulae astronomers photograph with telescopes. Others remain hidden. Dark molecular clouds where the earliest stages of star formation are still unfolding behind thick curtains of dust. From far away, these regions would appear almost like faint embers scattered across the spiral arms. A cloud begins to collapse. A cluster of stars ignites. Light spreads outward into the surrounding gas. Then slowly, over millions of years, the cloud disperses and the cluster drifts away. Elsewhere, another cloud begins the same quiet transformation. And this pattern does not belong only to the Milky Way. Astronomers observing distant galaxies see the same process repeating across the universe. In nearby galaxies like Andromeda, vast clouds of gas stretch along the spiral arms, forming new stars in much the same way as they do here. In irregular galaxies, star-forming regions appear as bright knots scattered across drifting gas clouds, and in some galaxies, especially those undergoing collisions or gravitational interactions, enormous bursts of star formation can ignite across huge regions at once. Yet, despite all these differences, the basic ingredients remain remarkably consistent. Cold gas, dust grains, gravity, time. From those simple ingredients, galaxies construct their stars again and again. It's easy to imagine the universe as something distant and separate from our lives here on Earth. But the connection runs much deeper than we might expect. The sun itself was once part of this process, long before Earth existed. Before oceans formed or continents appeared, the material that would eventually become our planet drifted through a molecular cloud in the Milky Way. Gravity gathered that material into a dense core. A protostar ignited at its center. A disk of gas and dust spread outward around the young sun. Inside that disk, microscopic particles began colliding and sticking together. Over millions of years, those particles grew into rocks, then planetesimals, then the early planets of our solar system. The Earth formed from the quiet accumulation of those fragments. The oceans condensed from water, carried by icy bodies that formed within the same disk. The atmosphere slowly developed as the young planet cooled and evolved, and eventually, on the surface of that planet, chemistry became complex enough for life to appear. All of that history traces back to a cloud of gas and dust drifting through the spiral arms of the Milky Way, a nebula, and that realization changes the way we can look at the night sky. When we see distant nebulae through telescopes, faint glowing clouds spread across the darkness. We are not just looking at beautiful objects far away. We are seeing environments where the same story is beginning again. Inside those clouds, new stars are forming. Disks of gas and dust are spinning around those young stars. Tiny particles are colliding, building the earliest pieces of future worlds. Some of those worlds may remain barren and silent. Others may develop oceans, atmospheres, or landscapes shaped by geological forces. The universe does not decide these outcomes in advance. It simply creates the conditions where they might unfold, and it does so through processes that are patient, gentle, and almost invisible at first. cold gas drifting through space, gravity slowly gathering matter, dust grains colliding softly inside rotating disks, stars igniting deep within clouds of gas and dust, the quiet architecture of the cosmos assembling itself piece by piece. And even now, far beyond the reach of our eyes tonight, countless stellar nurseries continue their work. Molecular clouds drift through the spiral arms. Dense cores are forming within them. Protostars are glowing faintly inside dusty envelopes. Disks are spinning around newborn stars. Tiny grains are meeting and clinging together, beginning the slow process that may one day build entire planetary systems. The universe is still building new suns, still shaping new worlds, still gathering matter into fresh forms, one nebula at a time. And as the Milky Way continues its long journey around the center of the galaxy, these quiet processes will keep unfolding for billions of years to come. Clouds will gather, stars will ignite, planets will slowly assemble from dust, and the galaxy will continue renewing itself in this calm and patient way. If you ever find yourself looking up at the night sky, perhaps on a clear and quiet evening, it can be comforting to remember that many of the stars shining there began their lives in places just like these. Hidden clouds drifting between the stars, cold, dark, and almost invisible, yet quietly gathering the ingredients for new suns. And even now, somewhere out there, beyond our sky, inside a distant molecular cloud, slowly turning in the spiral arms of the Milky Way, gravity is gently drawing atoms together. A dense core is forming. A protostar is beginning to glow, and the earliest light of a future star is slowly, patiently on its way. And if we stay with that image for a moment, a quiet molecular cloud drifting through the spiral arm of the Milky Way, it becomes easier to notice how gentle the entire process truly is. Nothing in a stellar nursery rushes. The gas moves slowly. The temperatures are low. Even gravity, which ultimately shapes everything inside the cloud, works with extraordinary patience. A molecular cloud may drift for millions of years before the first dense core begins to collapse. Then another few 100,000 years may pass before a protostar grows warm enough to glow clearly in infrared light. And even after that first glow appears, the young star still spends a long time gathering material from the surrounding disk. Compared with the pace of everyday life on Earth, it is almost impossible to grasp. Human civilizations rise and fall in only a few thousand years. Mountain ranges take millions of years to rise and erode. But the formation of stars often stretches across timescales even longer than that. It reminds us that the universe is comfortable working on rhythms far slower than our own, and yet the results of that patience are visible everywhere. Every bright star in the night sky once followed this same quiet path. Long before it began shining across the galaxy, it spent its earliest chapter hidden inside a cold cloud of gas and dust. Some stars formed in crowded clusters where hundreds of young suns ignited together. Others formed more quietly, emerging from smaller pockets of gas deep within molecular clouds. But regardless of the environment, the beginning was almost always the same: a slight gathering of matter, a dense core forming in darkness, a protostar warming at the center of a collapsing cloud, then a disk appearing around the young star. where tiny grains of dust begin their slow dance of collisions. And from those quiet beginnings, the rest of the system unfolds. The star eventually stabilizes, shining steadily for millions or billions of years. Planets may form in the surrounding disk. Asteroids and comets may remain as leftover fragments from the early stages of planet formation. In time, entire solar systems emerge, all from a cloud that once drifted almost invisibly between the stars. It may seem like a delicate process, and in some ways it is. Young stars can strongly influence their surroundings. Their radiation can erode nearby clouds. Their winds can push gas outward. Sometimes massive stars end their lives in supernova explosions that dramatically reshape nearby regions of space. But even these energetic events ultimately feed the same long cycle. Gas returns to the galaxy. Dust grains drift through interstellar clouds. Molecules form on cold surfaces. Gravity gathers matter again. Another stellar nursery begins. Over billions of years, this cycle slowly builds the structure of galaxies. The Milky Way itself has been forming stars for most of its history. Some regions of the galaxy are older and quieter now, containing stars that formed billions of years ago. Other regions are still rich with cold gas, where new nebulae continue forming today. In those regions, the story we have been exploring continues quietly. Molecular clouds drift through the spiral arms. Dense cores appear inside them. Protostars glow faintly within dusty envelopes. Disks of gas and dust spin gently around the newborn stars. Tiny grains collide, forming the earliest fragments of future planets. If we could travel far enough across the galaxy, we would find these scenes repeating again and again. A glowing nebula in one direction, a dark molecular cloud in another, a young cluster of stars just emerging from its fading nursery. The galaxy is full of these quiet transformations, and although the distances between them are vast, the processes connecting them are beautifully simple. Cold gas, dust grains, gravity, time. From these few ingredients, the universe builds stars, and from those stars come the light and energy that shape entire planetary systems. It's easy to miss how remarkable that simplicity really is. The universe does not need complicated instructions to create the structures we see around us. It simply allows matter to follow the gentle rules of physics. Gravity gathers, gas cools, particles drift together, and over immense stretches of time, the results appear. New suns, new worlds, new possibilities unfolding somewhere within the spiral arms of the galaxy. Even now, while we sit here quietly listening, the same process is continuing far beyond our sky. In a distant cloud of gas and dust, gravity is slowly drawing atoms together. A dense core is forming. Deep inside that cloud, a faint protostar may already be warming. Its light has not yet escaped the thick layers of gas surrounding it, but the process has begun, and with enough time, perhaps a few million years, that hidden glow will become a star, a new point of light, joining the countless others that shine across the Milky Way, a star that began, like all the others, inside a gentle nebula, drifting silently through space. And in the next part of our journey, we'll begin to soften the lens again, widening our view of these nurseries and letting the quiet rhythm of star birth settle into something even calmer. If we allow our view to soften now, the details of the cloud begin to blur a little. Instead of focusing on a single protostar or a single disk of dust, we can imagine the wider landscape of the galaxy once more. Across the spiral arms of the Milky Way, enormous clouds of gas drift slowly through the dark. Some are thin and quiet, almost invisible except to sensitive instruments. Others have grown thick and cold enough to become molecular clouds, the places where gravity begins gathering matter into new patterns. Inside those clouds, the earliest stages of star formation unfold quietly. Dense cores form in shadowed regions of the gas. Protostars glow faintly inside dusty envelopes. Disks spin gently around young stars, carrying the dust and gas that may one day become planets. But from the outside, the cloud itself remains calm. There is no sudden motion, no loud announcement that something important is happening, just a slow gathering of matter that continues year after year, century after century, millennium after millennium. The universe is comfortable with that pace. It has always been. The stars we see tonight did not appear in an instant. Most of them began their lives millions or even billions of years ago, and many of the stars that will shine in the future have not yet fully formed. Their earliest stages are still hidden inside the dark molecular clouds drifting through the spiral arms. It can be comforting to imagine those quiet places, regions where the galaxy is patiently assembling its next generation of suns, atoms drifting together in darkness, gravity shaping the gas into gentle swirls and pockets, tiny grains of dust meeting and clinging together inside spinning disks. The beginnings are always subtle. If we could float inside one of these clouds, we might not notice much at first. The gas would be thin. The temperature would be extremely cold. Only a faint glow from distant stars might filter through the surrounding dust. Yet, hidden within that calm environment, gravity would be slowly gathering matter together. Somewhere inside the cloud, a dense core would be tightening, gas drifting inward, the center warming very gradually. And deep within that dark cocoon, a protostar would be forming. At first, its glow would be faint, visible only in infrared light. But over time, as more gas gathers around it, the protostar would grow warmer and brighter. Eventually, nuclear fusion would ignite in its core. The young star would begin shining steadily, joining the vast population of stars already spread across the galaxy. Around it, a disk of gas and dust would continue evolving. Inside that disk, microscopic grains would collide softly again and again. Clumps would grow, fragments would gather into larger objects, and perhaps, over millions of years, planets might begin forming from those fragments. Some of those planets might remain quiet and frozen. Others might become warm worlds orbiting their young sun. The possibilities spread outward from the same quiet beginning. A cloud, gravity, time. When astronomers observe nebulae through telescopes, they are often witnessing these early chapters of cosmic history. Glowing gas illuminated by newborn stars, dark molecular clouds hiding dense cores within them, jets of gas streaming outward from protostars, tiny disks silhouetted against the bright background of a nebula. Each of these scenes reveals a different stage in the long story of star formation, and yet even the brightest nebula is only a brief moment in that story. Over millions of years, the gas will disperse. The young stars will drift away from one another. The cluster will gradually spread across the galaxy, The stellar nursery will fade, but the stars themselves will remain. Some will shine quietly for billions of years. Some will evolve into red giants and eventually shed their outer layers back into space. A few will end their lives in brilliant supernova explosions, scattering heavy elements across the galaxy. Those elements will mix with new clouds of gas, and eventually, the cycle will begin again. A new molecular cloud forming, new dense cores appearing, new protostars glowing inside the darkness. The universe rarely stops building. Even now, far beyond the reach of our eyes, countless stellar nurseries are continuing their slow work. Across the Milky Way, new suns are quietly forming, and if your thoughts drift for a moment, that's perfectly fine. These processes do not depend on our attention. They continue whether we are watching or not. Inside distant clouds of hydrogen and dust, gravity is patiently gathering matter together. A faint glow is beginning somewhere deep within a dark nebula. A star that does not yet exist is slowly taking shape, and the galaxy, calm and ancient, continues its quiet work of creating light. If we let the image grow quieter now, the galaxy itself begins to feel almost like a calm landscape, not a place of sudden motion, but of slow changes unfolding over immense spans of time. Across the spiral arms of the Milky Way, clouds continue drifting through the darkness. Some of them remain thin and quiet, barely gathering into anything noticeable. Others slowly become colder and denser until gravity begins shaping them into molecular clouds. Inside those clouds, the earliest hints of star formation quietly begin. It doesn't look dramatic from the outside. The cloud may appear almost unchanged for thousands of years, even across human history. Very little in the cloud would seem to move at all. But inside, the slow work continues. Molecules drift through the gas. Dust grains float silently between them. Gravity gathers tiny pockets of matter into slightly denser regions. And over very long stretches of time, those small pockets begin their inward collapse. A dense core forms deep inside the darkness of the cloud. A faint warmth appears. A protostar begins. It may take hundreds of thousands of years for that small glow to become strong enough for astronomers to detect clearly. Even then, the young star remains wrapped inside layers of gas and dust, but eventually the star will emerge. Its light will begin illuminating the cloud that formed it. The surrounding nebula may glow softly as hydrogen gas becomes energized by the star's radiation. Stellar winds will begin pushing the surrounding material outward. Gradually, the cloud will thin. The nursery will fade, and the young star will continue shining on its own. Around it, a disk of gas and dust may still remain. Inside that disk, tiny particles may continue drifting together, building the earliest fragments of future planets. Some of those fragments may grow larger. Some may remain as asteroids or comets. Over millions of years, the architecture of a planetary system may slowly take shape. But the beginning of all of it remains almost invisible. A cold cloud, a faint gathering of matter, gravity patiently shaping the gas. It is the quietest kind of creation, and this process is happening right now in many places across the galaxy. Astronomers studying the Milky Way have identified thousands of molecular clouds drifting through its spiral arms. Some are already forming stars. Others may not begin collapsing for millions of years. Still, others may pass through the galaxy, without ever forming stars at all, slowly dispersing back into the wider interstellar medium. Each cloud follows its own path through the galaxy, yet the overall pattern remains steady. Clouds gather, stars form, gas disperses, then new clouds gather again somewhere else, across billions of years. This cycle has slowly filled the Milky Way with its vast population of stars. Some of those stars are ancient, formed when the galaxy itself was still young. Others are far younger, only a few million years old, and many more stars have not yet begun their lives. They remain hidden inside cold clouds of gas and dust, where gravity is still shaping the earliest stages of their existence. If we could somehow speed up time and watch the Milky Way evolve over millions of years, we might see star-forming regions appearing and fading across its spiral arms like gentle pulses of light, nebulae glowing brightly for a while, clusters of stars emerging from the clouds, then the clouds dispersing again. Elsewhere, another region beginning its slow transformation, the galaxy quietly renewing itself. And while this immense process unfolds across unimaginable distances, it remains connected to something very familiar. The sun above us, our own star, followed the same path long ago. Before it began shining in the sky, it was hidden inside a molecular cloud, much like the ones astronomers observe today. A dense core formed, a protostar ignited, a disk surrounded the young star. Dust grains collided and slowly assembled into the early planets of our solar system. Earth formed from those fragments. The oceans condensed. The atmosphere developed. Life eventually appeared. All of that began inside a drifting nebula, and tonight, far beyond our own sky, new nebulae continue their quiet work. In some distant molecular cloud, atoms of hydrogen are slowly gathering together. Gravity is shaping the gas. A dense core is tightening. Deep inside that core, a protostar may already be warming, still hidden, still wrapped in its dusty cocoon. But the process has begun. A new star is slowly finding its way into existence, and the galaxy, vast and patient, continues building its future suns, one cloud at a time. And as we drift a little farther outward in our imagination, the details of any single cloud begin to soften again. Instead of one nebula or one young star, we can picture the Milky Way as a vast and slowly changing landscape of gas, dust, and light. Across its spiral arms, enormous clouds move gently through the darkness. Some of them remain thin and quiet, barely gathering into anything noticeable. Others slowly cool and thicken, becoming the cold molecular clouds where star formation may begin. From far away, these clouds would appear almost like faint shadows drifting through the galaxy. And inside some of them, gravity begins its quiet work once more. Atoms drift together, molecules gather, dust grains float through the cold gas, carrying delicate layers of ice on their surfaces. Tiny pockets of slightly denser gas appear. These pockets grow slowly, almost imperceptibly, over long stretches of time. Eventually, they become dense cores. Inside those cores, gravity continues pulling matter inward, tightening the gas into a smaller and warmer region. A protostar begins to glow faintly inside the darkness. At first, the light is hidden, wrapped inside thick layers of gas and dust. But slowly, as the young star gathers more material, its warmth increases. Jets of gas may stream outward from the poles of the star. A disk of gas and dust spins quietly around it. Inside that disk, dust grains drift together and begin forming the earliest fragments of future planets. From the outside, the cloud itself may still appear calm and silent, but inside, an entire solar system may be slowly assembling. It's remarkable how small the first steps are. A grain of dust drifting through space, a second grain meeting it gently, a tiny clump forming, then another collision, and another. Over millions of years, these small events accumulate into something much larger. Planets, moons, asteroids, comets, the architecture of solar systems quietly emerging from the simplest beginnings. And once the young star grows strong enough, its light begins reshaping the cloud that formed it. Radiation spreads outward. Stellar winds push against the surrounding gas. The nebula slowly opens, revealing the cluster of young stars shining inside. Eventually, the cloud disperses altogether. Gas drifts back into the wider galaxy. Dust spreads through interstellar space. The stellar nursery fades, leaving the newborn stars traveling through the Milky Way. Those stars will continue their long journeys for billions of years. Some will remain small and steady, shining quietly like our sun. Others will grow into massive stars that burn brightly and live shorter lives. A few will eventually explode as supernovae, scattering heavy elements back into space and helping prepare the next generation of nebulae. And so, the cycle continues. Gas gathers into clouds. Clouds form stars. Stars return gas to the galaxy. Then new clouds begin forming once more. Across billions of years, this patient rhythm slowly builds the structure of the Milky Way. And tonight, while the sky above us appears still and quiet, the same process continues far beyond our sight. Inside distant molecular clouds drifting through the spiral arms, gravity is gently gathering matter together. Dense cores are forming. Protostars are glowing faintly within dusty cocoons. Disks of gas and dust are spinning slowly around newborn stars. Tiny grains are colliding, beginning the long process that may one day create entirely new worlds. The universe is still building its stars, still shaping new solar systems, still gathering matter into fresh forms, all of it beginning in the same quiet way. A cloud drifting through the darkness, gravity patiently pulling atoms closer together, a faint glow appearing deep within the cloud. The earliest light of a new star slowly finding its way into the galaxy. And if your mind begins to wander now, that's perfectly fine. The galaxy will continue its quiet work whether we are watching or not. Clouds will gather, stars will ignite, nebulae will appear and fade again across the spiral arms. The Milky Way will keep turning slowly through space, carrying its stars and clouds with it. And somewhere out there tonight, inside a cold, drifting nebula, a star that does not yet exist is patiently beginning. And by now, the details of nebulae and protostars may already be fading gently into the background of your thoughts. That's perfectly all right. These stories of cosmic clouds were never meant to demand attention. They are slow stories, quiet stories, the kind that can drift softly beside you while the mind grows calmer and the body prepares for rest. Across the Milky Way tonight, the process we've been exploring continues without hurry. Molecular clouds drift through the spiral arms like vast, cold seas of gas and dust. Inside them, gravity gathers atoms into slightly denser regions. Dense cores form. Protostars warm slowly inside dusty envelopes. Disks spin around those newborn stars. Dust grains meet and cling together. The earliest fragments of future worlds quietly begin, all of it unfolding across millions of years, far beyond the pace of ordinary human time. And yet, every star we see in the sky tonight began in places just like these, long before our sun warmed the earth, long before oceans formed, long before life appeared. Our own star was once hidden inside a drifting nebula in the Milky Way. A dense core formed, a protostar ignited, a disk of gas and dust surrounded the young sun. Tiny particles collided and slowly gathered into the early planets of the solar system. Earth formed from those fragments, and much later, after billions of quiet years, we arrived beneath the sky those processes created. So when we look at distant nebulae through telescopes, we are not only looking outward into space. In a way, we are also looking backward into the earliest chapter of our own cosmic history. The same quiet beginning, a cloud, gravity, time, and from that gentle beginning, stars emerge, solar systems assemble, galaxies slowly fill with light. Even now, somewhere far beyond the reach of our eyes tonight, new nebulae are quietly preparing the next generation of suns. Deep inside those clouds, protostars are warming, disks of dust are turning, tiny grains are meeting and sticking together, beginning the slow work of building planets that may not fully form for millions of years. The universe does not rush. It gathers matter patiently, cloud by cloud, star by star, across billions of years of calm cosmic time, and the Milky Way continues turning through space, carrying its stars and nebulae along with it. Somewhere within its spiral arms tonight, a cold molecular cloud drifts quietly through the darkness. Gravity is gently drawing atoms together. A dense core is forming. Deep inside that hidden region, a faint warmth is beginning. The earliest light of a new star, slowly, patiently coming into existence. And while that distant star begins its long life, you don't need to follow every detail anymore. If your thoughts have begun to wander, that's completely fine. If you've missed a few sentences, nothing important has been lost. You can simply rest here for a moment, letting the story of the galaxy continue quietly in the background. The nebulae will keep drifting. The stars will keep forming. The Milky Way will continue its slow turning through space. And you can let the rest of the night unfold just as gently. Thank you for spending this quiet time here on the Sleepy Science channel. And if you're already drifting towards sleep, you can simply allow that to happen. There's nothing more you need to do now. You can rest. You can let the universe carry on its calm and patient work. And you can let sleep arrive whenever it wishes.